My name is Tim Pleskac. I'm the president of the Society for Mathematical Psychology. I'm here interviewing Jerome Busemeyer for the 2023 Senior Fellow Award. And so we're going to have a conversation a little bit about his history in mathematical psychology and just his scientific career. So welcome, Jerome.
Well, thank you. And I want to say I'm very honored to receive this award. I know in this field there's so many outstanding scientists, and so I feel, kind of lucky but very honored to receive this award.
Yeah, there are, and you stand out. So congratulations. So I thought I'd actually start kind of getting to know and helping everyone get to know who you are. So you got your PhD in psychology from the University of South Carolina. What drew you to psychology, and how did you end up in a PhD program there?
Well, I think ever since I was in high school I was interested in psychology, but I began my interest in clinical psychology until I went to undergraduate and I took an introductory psychology course. Also, I worked in the 8th floor of a psychiatric ward. So both of those experiences, the 8th ward showed me how little we know about clinical psychology. And the introductory psychology class taught me that there's a science of psychology. So I rapidly switched to interest in the science of psychology. But when I was an undergraduate, I worked with Bill Dember at University of Cincinnati. And he did actually work in backward masking and perception. And so he wrote me a letter of recommendation, and it was picked up by Lester Lefton at University of South Carolina. Lester also worked in backward masking. And so Lester recruited me because I worked with Bill Dember. But after a year working with Lester, which was really good, I really wasn't interested in perception. I was really more interested in, motivation at the time. What motivates people. So I actually switched my advisors at that time from Lester Lefton to Roger Black. Mm-hmm. But Roger Black started having some problems midway in my career, so I became a little bit on my own midway in my PhD, a little bit of an orphan.
And was the University of South Carolina? How did you end up at South Carolina? Just
because of Lester Lefton.
Because of Lester. Okay.
He was at South Carolina and he recruited me there and gave me a position, and so.
And that actually brings me to the kind of so you were working with Roger Black, but kind of started to look around. So that's kind of where I thought where your original area of study wasn't in mathematical psychology. So how did you get started in math psych? What was after that?
Well, early on, when I was just beginning my career, I thought, well, I wanted to do psychological science, and I thought, well, there's 2 ways to do that. One way is to go into neuroscience. The other way is to go into mathematical psychology. And I was familiar with Estes' work in learning theory at the time. And I thought, well, neuroscience might require, I'm not really good at memorizing things like parts of the brain and all the neurotransmitters. So I thought, I'm better at deriving things because I don't have to remember. I just, derive it if I can't remember. So I thought I'd be better off in doing mathematical psychology. And so I got interested in mathematical psychology because I wanted to do a serious science. And I thought that was making psychology more mathematical would increase the strength of its science.
And but there wasn't anyone at South Carolina that was doing this?
No, I mean, like I said, Roger Black, he was actually a student of Kenneth Spence. This is Kenneth Spence's last student. And he was an animal learning theorist, so I started out in animal learning. But he started having troubles, and I got tired of running animals. I got bit by rats too many times. But anyway, I decided to move into human decision making. And anyway, Black was having some troubles, and so I started working on human decision making by myself. And I was kind of, like I said, an orphan. But, fortunately, I contacted Tom Walston and Amnon Rappaport at the University of North Carolina, which wasn't that far away, kind of a couple hours drive. And they were, the first and foremost benefactors who helped me get my career started. And I was like an orphan, like I said, but they helped lead and guide me. And I was feeling a little bit lost, but they really adopted me like fathers and took care of me and took responsibility for me. And so until I got my postdoc.
So you drove up?
Yeah, I would drive back up and forth to visit with them and present my research to them. and they would be very generous. Tom had me stay over his house a couple of times with his family, and so they put me on the starting line in my career, and so I didn't have to suffer the Waterloo incident and Napoleon's Grand Army did.
And so Amnon at that time, he was probably doing some sequential sampling models?
Yeah, he was. He was working on deferred decision-making, sequential sampling.
So is that how you kind of started to think about the sequential sampling
Well,
models?
I was interested in choice behavior, and I was reading Este's work on choice behavior, and he did some work on Markov models of choice behavior, but they weren't sequential sampling. And so I got interested in sequential sampling because I went to a psychonomics meeting and I heard one of Steve Link's talk, and Link was talking about sequential sampling. I thought that's a better model than Este's. Este's model was like a runs model. It was like you look to the right and you start taking steps towards taking that alternative, but then you might change your mind and then you switch and then start looking to the left, and then you start taking steps to the other alternative. And I was working with that model for a while, but I didn't like it. It didn't accumulate, because as soon as you switch, you lose all the information.
Oh, I see.
And I really like the sequential sampling idea that you're accumulating. And so I became interested in Steve Link's work at first. And then I also, of course, quickly ran into Roger Ratcliffe's work. And so those two bodies of work got me interested in sequential sampling models and random walk models and diffusion models of decision making.
So, and what kind of stuff came out of, did you have any work that came out of working with Amnon and Tom that you enjoyed?
I never published anything with Tom, actually. It's funny. But I did publish things with Amnon on deferred decision making. I have a paper published in Journal of Mathematical Psychology. We worked together on, it's more like that paper was concerned with optimal stopping boundaries when the information cost is increasing during sampling, which happens to be a kind of a hot topic right now. And
people should read this paper, right?
Yeah, well, Shadlin actually mentioned that paper in some of his works.
Yeah, so this brings me, actually, I'll come back to the sequential sampling questions. In general, you went into mathematical psychology because it was rigorous, and I guess I'm always interested in this. From working with you, I know that you can get pretty far with linear algebra and stochastic processes. So what came first for you? What's easy? Is the psychology easy or is the math easy?
Actually, I think it was easier for me. The math was easier. I used to read some of the psychology papers, which were just verbal and conceptual, and you get really sleepy and not follow the logic. So I got really attracted to mathematical psychology articles because I could just, rigorously follow the reasoning and the argument, and the predictions that they're making. And I had a lot of struggles just reading, these conceptual papers and the intuitive logic they were using. So actually, the math came easier for me. It still comes easier for me.
And did you start to build up your training that way? Did you, when you're at Cincinnati, did you get a lot of math background there, or did you kind of start to build up math as you realized?
I took math in Cincinnati. I had a calculus class there, but it wasn't one of these. It was like a calculus for business students or something. But I went to South Carolina and I retook a 5-hour calculus class for 3 years, an advanced version of it. And boy, that really trained my mind. I think taking a really solid calculus class can really improve your thinking a lot.
Okay.
So that was. But then after that, I had a good teacher at the time in psychometrics at South Carolina, Dick Kleinecht. He actually went into industry, but he was really good. And of course, psychometrics, a lot of the stuff like factor analysis and multivariate statistics, they require a lot of linear algebra. So we went into a lot of linear algebra. I had linear algebra in the calculus class, but then I had a lot of linear algebra with this in the psychometric training, and then I've had linear algebra training all my life, I think.
So you just started to learning from psychometrics and then started to understand a little bit more. What about stochastic processes? Is it the same thing? Yeah,
well, I had to do stochastic processes because I got interested in choice modeling, and these choice models like Estes and Ratcliffe's and Link's models are all stochastic processes. But I got my first interest in stochastic processes. This is way back, maybe when I was almost maybe still an undergraduate or just starting a graduate student. I read the ABC of Mathematical Learning, Atkinson, Bowers, and Crowther's book. And it's a kind of a simple mathematical learning book, but it's really a good book, and that's really got me started in stochastic modeling.
Huh.
I mean, early on, you know.
So did you read Link's books, Link's papers?
I read Link's papers, and then I was taking, you know, courses in the math department on stochastic processes, and I was reading Feller and those kind of books, you know.
Yeah.
So I learned a lot of stochastic processes. My favorite book, by the way, I have to say, is Bhattacharya and Waymeyer.
Oh, yes.
Stochastic processes. But he was Bhattacharya as a professor here at IU.
Is he at IU? Huh.
I think he might. I don't even know if he's still alive, but he's retired. He was here.
I know you referenced that book.
Yeah. Yeah.
Well, so what would you tell new people? All right, so I've been new people either from psychology that want to learn how to do mathematical and computational modeling, or people from more math and computational backgrounds. How should they get into the field?
Well, I mean, I recommend psychologists take as much math as possible. Actually, that reminds me, I'm coming back to something I remembered. One thing that got me going in mathematical psychology was the Atkinson, Bowers, and Crawford's book. But the other book was the Coombs, Dawes, and Tversky book. I think it's just called Mathematical Psychology.
Mathematical Psychology.
Isn't that kind of an undergraduate? That was an outstanding book. And it went into measurement theory and signal detection theory and learning theory. And I really learned at the beginning a lot from those two books. But then after that, you know, I was taking, you know, one thing was funny. I met Jim Townsend and Greg Ashby at a math psych meeting, and I was telling them the courses I had had when I was just a first-year PhD student, or early on. And they said, well, you need to take courses in differential equations too. So they were the ones that got me.
They got you going there?
Well, they got me going in differential equations. But yeah, I think those were all critical, you know, matrix algebra, linear algebra, you know, stochastic processes, differential equations. I would always recommend this for a young student who wants to do serious theoretical work, whether it's in cognitive science or neuroscience.
Okay.
You need that.
But you also have to kind of take and build up your theory, but understand the modeling.
Yeah.
So I guess that I'll come back to the sequential sampling. So, you know, I was thinking about this. So if I ask people in the field what they associate decision field theory with, I was thinking what they would say. They'd say Jerome Busemeyer, Jim Townsend. They'd probably think 1993, complicated, and context effects. So what's the origin of decision field theory? Where did that come from? So you started in sequential sampling models, and how did that come to be?
Yeah, I did my dissertation on sequential sampling models, and I actually worked when I was an assistant professor on developing sequential sampling models. That was when I was at Purdue. And of course, Jim was at Purdue. But Jim and I started having lunch together. For a couple of years, we would have lunch together for once a week for a couple hours. And we wanted to construct a new theory of decision making that would be based on psychological principles rather than economic principles.
Okay.
And one that would be mathematically rigorous and dynamic and stochastic. So we spent, you know, lunches a couple hours a week for a couple of years. Finally, Townsend told me, look, you know, let's quit talking. Let's start writing. So I had to start writing. That meant you start writing. Anyway.
No chalkboards at the lunch, or just?
We didn't have chalkboards. We even had to walk. We didn't bring paper even. We had to usually work with napkins. Now, the thing about that 1993 paper was interesting is when we first wrote it, we started with a very general model, and then we derived all these special cases. It's kind of like the way mathematicians like to do. They state the general thing and they show you these example special cases. So that's how we originally wrote the theory. It wasn't rejected, but we had to do many revisions.
Oh, really?
And it's several revisions. But in the revisions, we decided to reverse the whole thing. So then we started with the simplest possible model and added one step at a time.
Huh.
And that was successful.
So the psychologists like the simple to the more
And
complex.
they want to know. They want to have a reasons why, like, okay, here's the simplest model. Then why add this step? And you tell them why that step. Then why add this next step? And then we tell them why we add the next step. Now why in the world would anybody think that paper's complicated? I think we really laid it out straightforward, simple.
Because the conclusion ends up being you need a more complex model, I guess.
The conclusion, the model at the end was a little bit complicated, but not as bad as the models these days.
Yeah.
It's a lot simpler than some other models.
Well, that might be a different conversation, right?
Yeah, right.
So I have, I guess the other thing that I was thinking about right, is something that really stands out. Like decision field theory was a whole research program, and there's people still know working on it. And at some point you stopped, or you haven't really stopped, but you switched, and you went to think about quantum models. And I think that's really interesting about your career. You've actually really, in my opinion, started two different or multiple research programs. So, and obviously everyone's aware of your work in this area. So my question to you is, how has quantum models changed your career?
Well, let me back up a second, a little bit on decision field theory.
Sure.
Yeah. So, I was still working on it with, Joe Johnson and I wrote a paper on preference reversals, and then I started working on the quantum stuff, and I started working less on decision field theory. But I had so many good students and colleagues. So, Joe Johnson was continuing working on it. Jorg Rieskamp did a lot of really good work on decision field theory. Of course, Adila did a lot of really good work on decision field theory. And you did some work on decision field theory. And like somebody that from Carnegie Mellon, I was on his committee, Sudeep Bhatia did a lot of work on decision field theory. So I had a lot of people covering for me.
So you just felt like you had the field.
That was going by itself already. So
it was getting boring?
Well, it wasn't getting boring. Okay, the reason how I got into quantum theory is a kind of interesting story. So at first, it began with In-Jae Myung. He was In-Jae at the time, now he's Jae Myung. He was one of my first graduate students. Adila and In-Jae were my first students. But when In-Jae came from Korea, and he had a degree in physics. And he first came into my office, and he was sitting at the blackboard, and he was going on and on, because he had a physics background, about quantum theory. And he was putting these equations on the board and saying how beautiful it is, and they use these complex numbers. I didn't know anything about quantum theory. I don't have a strong background in physics. So I just was curious, and I started just reading popular books on quantum theory, like Penrose's Emperor's New Mind and things like that, Brian Greene's work and things like that. And I was reading and spending a lot of time reading these things. And my wife noticed this, and my wife, Mei Juan, and she's so I have to tell you about my wife. She played a pretty important role in getting this quantum program started seriously.
Really?
Yeah, right. Yeah. Anyway, I have to tell you, my wife is, first of all, my wife is a beautiful woman. She's very intelligent and talented and kind and strong and wise woman. And she has a keen sense of judgment about the essence of things. And anyway, she was like the first person who encouraged me. She's like, look, you're spending all this time reading this stuff. Why don't you take it serious? Why don't you, start doing some serious research on this?
So both cases. So Jim told you to get serious and write the paper, and now Mei Juan also is like, you got to stop and write the paper now.
Right. Yeah. So she wanted me to find a new way for the field of cognitive science. She once told me the roads of cognitive science seem to be getting narrower and narrower. She kept seeing all this work on more and more sequential sampling, every version of it. So you got to consider opening up a brand new road and break out of the bottleneck, she told me. And so with her inspiration and her behind me, I began formulating this new direction for the development of quantum cognition.
So Mei Juan played a pretty big role.
Yeah, right.
How did it change your? So let me go back. So how has it changed your view of cognition? So what happened?
When I first started, when I started reading it more seriously, I started reading some quantum computing books. I read Feynman's books. They really opened my eye up. But I started realizing that quantum theory is, of course, it was invented in physics to solve puzzles in physics. But actually what they invented is a whole new kind of probability theory. In fact, a probability theory that's more general than our classical probability theory. So classical probability theory is based upon these Boolean axioms like commutativity and distributivity. And quantum theory, though, relaxes some of these axioms. And so, and I thought these relaxations are important because, for example, their behavior is non-commutative and non-distributive in some of the judgments that they make. And so I started realizing quantum theory is a whole new kind of probability theory. And I thought that was so fundamental because I never realized there's a whole different kind of probability theory out there. Now I realize there's a whole field of generalized probability theories. Quantum theory is maybe just one of them, maybe the closest to classical. But it's kind of like, when you're a young kid and you're learning Euclidean, you're learning distance and theories of distance, and you learn Euclidean distance, and you think that's the only theory of distance. You don't realize there's other theories of distances out there.
Yeah.
And you just change the axioms and you get a new theory of distance. Well, von Neumann changed the axioms of classical theory and developed quantum theory. And so it was a fundamental new direction, I thought, to try to build models based upon new principles. So that's what I thought was so interesting to me. It got me, so seriously involved in it. But I have to tell you a story. I mean, one of the people really strongly supporting my work in quantum theory is Rich Schifrin. He's always been a critic, but he's always been a strong supporter. Even like when I'm down, he'll give me encouragement. But I have this story I have to tell. When I first started developing quantum theory, and I wanted to write a book so that it become more accessible to people. And when I was writing this book, I derived a theorem or a property of quantum theory for question orders. We call it the QQ equality. It's concerning when you ask people questions, you ask them A, then B, then versus you ask the question in the opposite order. There's a certain powerful constraint that the quantum model must predict. It's a very simple linear constraint, and it's an exact equation that must be satisfied, and it's parameter free, and it's completely general for any dimension of the space or any kind of rotation operators that you use in quantum theory. So it was a very general prediction, and so I was so happy to get this really general prediction. But then you get scared. You're vulnerable. I mean, I was writing this book, and we call it the QQ equality. And this QQ equality is easy to test. You just need to get some data where there's question orders, and you can plug the data, and it takes 1 second to test the theory. And so I was really scared.
How long did it take you to press the button?
Yeah, well, we got the first data set in. It was one of these data sets from David Moore, Gallup poll data set on Clinton and questions about Clinton and Gore.
Yeah.
But I got the data set in, and it's only 8 numbers. You put it into the computer, and you push. That's a simple formula. Push this button, and you find out the theory works or not. I pushed the button, and my whole theory is at stake, and this whole proof I was so proud of is at stake. I pushed the button, and the answer came out. The answer was supposed to be 0.
Okay.
When this QQ equality holds, the answer is supposed to be 0, and it came out to be 0.00002. And I was so excited. I ran to Schifrin's office. I said, Rich, look, I derived this prediction from the quantum theory. We got this data. I put it in there, and the prediction's holding up to the 4th decimal place. He burst out laughing. Because he said, it's just an accident. It's just a coincidence.
Just do it again.
This will never happen again. But then I got the second data set. And so I got the second data. It was about Dolan Gingrich. It was a Gallup poll story. And I put that data in the equation. And it came out again. And it wasn't 0.0002, but it was 0.006. I said, wait, look, it worked again.
Yeah.
And so I ran back in Rich's office. And this time he says, look, quit fooling around just getting 1 or 2 table sets. Give me 100 data sets and see. And so that's how eventually Rich and I wrote this paper on this QQ equality. And so Rich has been a big supporter for a long time on the quantum side. He's always been a critic, good critic, but pushing, been a driving force behind me.
Well, actually, I in talking with you, it's reminding me how important the people around you are to your science. So I looked up some stats. So you've had 243 co-authors. Did you know that?
No. I didn't keep track of them. I think that's probably on Google, right?
Yeah, so somehow you have 243 co-authors. So so what role has co-authors played in your work? So I know you've written a lot of the papers and worked with them. How do you approach co-authors, and how does this kind of?
Well, I mean, it's more fun to do work with co-authors. I mean, I remember when I wrote the first paper on applying the quantum probability to the prisoner's dilemma game, and I published the paper in Cognitive Science. And Emmanuel Pathos read it. I mean, I didn't know Emmanuel.
Mm-hmm.
So he read this paper, and he emailed me, and he had a background in physics, but he's in cognitive science now. He was a student of Nick Chater's. But he wrote me, and he said, I'm really interested in this quantum stuff. I have a background in physics, but I have a question. I had a Hamiltonian that I used in this paper. What's your psychological justification for this Hamiltonian? So that's how he and I got started. Just like he picked up on my cognitive science paper, and ever since, that was maybe 2007 or something. So ever since then, Emmanuel and I have been collaborating on many projects, and he's always been a good collaborator. And we take turns, being the writer, but he's been a really good collaborator. We have many papers together. So he asked me that question about the Hamiltonian, and that paper was just published in Cognitive Science. And so we started working together to revise that paper to try to get it published. At first we tried to get it published in Science. We actually got it reviewed, but one of the reviewers complained that he had an alternative explanation that could account for the results without quantum. And then I proved that no, his explanation doesn't work. But Science says, no, we don't ever review things twice.
Oh man.
So then we tried PNAS, but we didn't get into PNAS either. We did finally get into Proceedings of the Royal Society. That was one of our first big papers. But we did finally publish in PNAS later on. But with your paper.
Did you get a justification for your Hamiltonian?
Yeah, we developed a good psychological justification based upon cognitive dissonance theory. Actually.
Okay.
Yeah.
Okay.
Yeah.
Okay. How does
But
friendship?
I mean that was Emmanuel. But of course, I've had so many. It's dangerous to start talking about individuals because then I'll go on and on about all of them. So but you're here, so I mean you're a great collaborator of mine. I mean, I remember you had a job offer at Ohio University and you decided to take a postdoc with me. I said, if you got a job, just take the job. Don't take a postdoc.
I think you said something like bird in the
bird in the hand's worth two in the bush. Well, you took the postdoc with me, and we wrote this beautiful paper together on two-stage model of signal detection. Actually, you wrote most of it. You did most of the work. Oh. I did help you come up.
Yeah, you had the idea. You said you should work.
That's a pretty high impact paper. But then since then, you invited me to come to
Berlin,
Michigan
State. Yeah, Michigan State. We did
and do a quantum. And one of your special talks, cognitive science talks.
Yeah, exactly.
And meet people and discuss my work with them. And you gave them all training in quantum cognition.
That one that was hard because the ritual there is that the person that invites has to give an introductory talk.
Yeah.
So I had to actually kind of wrap my head around quantum.
Well, that was good because then you got interested in quantum theory, and we've done some good quantum work together.
Yeah.
Yeah. And Jorg's kind of an interesting one because, just to mention, there's so many. I'm afraid I'm going to get some of my students upset. I can't mention all of them, but Jorg is interesting because. Jorg Rieskamp, because I sent Joe Johnson to NPI to work with Giga Renzer, and Giga Renzer sent Jorg to work with me. It was like an exchange program. And Jorg was working with us as a postdoc with me, and we did work on learning and decision making, and Jorg went on to do some great work in learning and decision making by himself. That's pretty well known. But he also got interested in decision field theory then, and he did some great work on decision field theory for me too. So
and he's still working on it.
Yeah, he's still working on it. So that's really good.
So I have a question. So I was thinking about the mentorship, and as we've kind of seen, and there's a long list, and it's hard to mention everyone.
Yeah.
And many of the students are quite successful. So what are some simple rules as a mentor that you might share for aspiring mentors?
I don't know. Everybody does it differently, So, but the way I tend to mentor my PhD students is, I first don't recruit a student to begin with unless I think they're really, really good. So I don't need lots of students. I just need a few good students. So usually the students I recruit, are pretty outstanding students to begin with. They have to have good math background to begin with too, and interested in mathematical modeling. So that's makes it easier up front for me. But and of course I hope they're interested in the work I'm doing. And but I often give my students lots of freedom to do whatever they want to do. You know, just another example, like Junie.
Junie Dai, yeah.
Dai Junie Dai. But anyway, the Chinese would be Dai
Yeah.
Junie. Anyway, but Junie, you know, I recruited him, and he had a background in physics, and I was doing quantum things at the time. So he came, and you know, I said, Junie, are you interested in working on these quantum projects? He said, no, I want to work on decision field theory and apply it to delayed discounting. I said, well, okay. And so, but he did some great work on delayed discounting and decision field theory.
Yeah.
So he was like developed the first, you know, sequential sampling model for delayed discounting using decision field theory. So that's just, yeah.
So give students freedom.
Yeah, I give them a lot of freedom. You know, I don't force them to do my own work, and so they develop a lot of independence that way, and can carry on by themselves in the future, right? And I also like, well, Jennifer's another example, one of my students, and when she first came to work with me, she did get interested in quantum cognition. She started working, and we wrote some really good papers together. But then I told her, look, Jennifer, you got to get a job, and so you can't just be quantum cognition. So I told her, you need to work on some of this traditional stuff, you know, like and make up your own theory, not necessarily decision field theory, but some other theory. She wanted to work with Heathcote and Brown, and they were working on the ballistic accumulator models, and so she developed this context model based upon the ballistic accumulator model. Yeah, so now she has a model competing with mine.
Yeah.
And so I was like, now she's trying to say her model's better than mine. Created a monster.
Well, it's competition.
No, it's good competition.
It's good competition.
Competition's good. And even Sudeep Bhatia,
Yeah.
he came up with his own theory. So I think that's good. Competition actually makes my model more popular because we get all these competitors, and
Yep.
you get into this field, and it makes a big buzz. I remember one time Elke Weber, she was an associate editor of Psych Review at the time, and she says, I'm getting so tired of reviewing these MAMA models. MAMA, what's a multi-attribute, multi-alternative model?
Mama months.
Everybody was submitting a new multi-attribute, multi-alternative model.
Huh. So simple rules. I guess I was actually also thinking one other question. I was thinking as we talked about your abilities in math. You once told me, I don't know if you remember this, that I should never lose my ability to run my own experiments. So what abilities do you think have made you a good researcher?
Well, I mean, of course, my mathematicals. I'm constantly learning new mathematics, and brushing up on my old mathematics. So I think that's really important. But also, I try to do as much of my programming myself as possible.
Yeah.
Except there was one period in time when I took NJ on as a student. He was so good. I'd let him just take care of some of the programming, do a lot of the programming for a couple of years, and I started getting rusty. And I'm like, oh man, I'm never gonna do that again. From now on, I got to keep my hands and make sure I'm doing a lot of the programming myself. So that's really important. Now, one thing though is I do a lot of my own programming for my computational modeling, but from my experiments, I've lost that. I've quit learning. I've lost my skills for designing experiments, or I rely on students actually, because everything's changed now. It's all on the web, and you do these online experiments, and
yeah, I was just talking.
I haven't picked that up.
I was just talking to my students, and I told them that you ran experiments, you programmed experiments, but
yeah, I don't anymore, but I did at some point. But that's
your 1985 paper is a really strong paper in that.
Yeah.
So what do you wish you could do better, though?
Well, I kind of miss being able to program experiments, because sometimes I might want to just get an idea and set it up on the web online, and I can't do that. I have to have a student do that. But I'm not doing so many experiments these days. I am letting all the students do the experiments.
Okay. So we've talked a little bit about different aspects. I have. So I did some other research on you. You've had over 22,000 citations. It's quite a lot. So I was curious.
A lot of self-citation. No.
So what were your goals when you set out to be a professor in psychology? What did you think, like when you started your career, And did you like, okay, I'm gonna work in decision making and create a new theory, or just what was the goal in the beginning?
I think the goal early on was to try to create my own theory. I thought that was the coolest thing, you know. I thought, you know, I saw people in my field, you know, like Estes or Luce, or those are my, you know, ideals, you know, and I wanted to be like them, you know, develop, you know, an important new theory. I thought that would be a big contribution that would, if it was a good theory, it would really maybe change the field, you know, make a difference, rather than just doing another experiment. And I always thought, like, you know, when I was a graduate student, when I was working on decision field theory, in fact, even before I worked on decision field theory, I was working on sequential sampling models of choice. And I submitted a paper to one of the journals, just like an experimental journal. And one of the reviewers, you know, the sequential sampling models of decision making didn't exist in the 1980s, you know.
Yeah.
They were all doing, you know, heuristics and biases, Kahneman and Tversky stuff. And one of the reviewers didn't understand the model and thought it was too complicated and said, look, I give you some advice. You're a young man. You're just getting started. I suggest you drop this and then you try to pick up this work on Kahneman and Tversky on heuristics and biases. That'll be, you know, much more popular. And I thought, no, it's just the opposite. If 100 people are working on this problem over here, I want to go a different direction and work on something entirely new that nobody's working on. Because if I go work with them on 100 other people, somebody's bound to find the same idea that I'd find. But if I go over on this other side and work on something totally new, like quantum cognition, nobody's working on that, then I can make a difference, discover something new.
You gotta take a risk.
Yeah, you'd have to take a risk. But yeah, my wife was behind me, pushing me. You've got to take this risk.
You have a really strong reputation in the field, and there are probably lots of things people want to know about you. But here's the one thing I think nearly everyone wants to know. So what's the origin of the quote that's in your email? Life is complex. It has both real and imaginary parts.
Well, I didn't steal it, but I borrowed it from a quantum computing book.
Really?
It was like in one of the chapters. Nielsen and Chuang they have a book. It's a very popular book. It's written in 2000, but it's still like the Bible of quantum computing. In one of the chapters, they have quotes on each chapter, and one of the quotes from the chapter was, you know, life is complex, it's got real and imaginary parts. So, yeah, I borrowed it from Nielsen and Chuang, but well, they listed as anonymous, so we don't know who created that saying. But I like that idea because even Einstein said that experience and knowledge is not enough for science. What science really needs is imagination. That's what makes science really work. Is you have to go beyond the knowledge and beyond the experience and into imagination to imagine a world that you can't necessarily see or know. And so that's why I like that you know, it's real and complex. It's real and imaginary parts, you know.
Is that some other advice you'd say? Is make sure young scientists set time aside for imagination?
Yeah, you need to have your imagination, and you have to have courage to follow it sometimes.
Yeah.
And you also have to have perseverance and persistence. You know, it's
Yes.
like when I first started working on both decision field theory and quantum cognition. Decision field theory, at that time, you know, 1980s and 90s, nobody in judgment decision making was working on those kind of models, and so I got a lot of trouble, you know, trying to, like, people didn't understand it. They didn't know why it had to be dynamic or stochastic. I mean, they were working with heuristic models or deterministic expected utility models.
Yeah.
And so I had to struggle for many years. In fact, my citation rate, my wife kind of makes fun of me, but my citation rate from when I started in 1980s till I met my wife, coincidentally, it was almost like undetectable from zero. But then after I met my wife, by coincidence, it started rising exponentially. About the same time I published some important articles. But yeah, I mean, I was like zero until I met my wife, and then and somehow she gave me good fortune and good future, and my citations started rising after that. But it took about 10 years for decision field theory to even be mentioned, you know. But people started picking it up and paying a lot of attention. Now it's pretty well known. And like quantum cognition, And quantum cognition, when I started that work, first people were like, oh, this is really interesting, curious, they're curious. How would you apply quantum theory to psychology, except quantum brain, which we don't do. We do use the quantum mathematics, not the
brain.
Not quantum brain. But they said, how do you use quantum theory in cognitive science? And they were curious. So at first my work was accepted as just because out of curiosity. But then when I started sending it to the major journals, and they say, wait a minute, you expect us to take this serious? And so now they were saying, look, you got to show more evidence than usual for this. So you've got to have stronger evidence than the usual paper if you want to publish. So we did. We tried to find strong qualitative evidence for the theory. And so then it went to a third stage where, people started taking it seriously and started testing quantum cognition. And they started doing experiments and actually showing some of our predictions were wrong, so we had to revise the theory, which is actually very good. Because now we've improved our theory as a result of people testing our theory and finding out where it was wrong. Costello's one of the people that done a lot of this work, but testing our theory. Anyway, so that's you got to persevere.
Persevere.
You got to have
imagination,
courage and you have to have imagination and perseverance. And struggle.
I was telling my students before we were talking about this interview, and I read some of the questions I was thinking about, and you've already kind of talked about this, but I think you have to have good support, right? So I know Mei Xuan, you've already mentioned this, but she's had an incredible impact on your life. How has Mei Xuan influenced your science?
Mm-hmm. Well, I think you asked me about that already because she is the one that
got you going on quantum.
Got me going on quantum.
Gave you the support.
But I had to tell you more about Mei Xuan because, she's a Chinese medical doctor. Even more than that, she's actually president of the American Menghe Chinese Medical Research Company.
Okay.
But anyway, I wouldn't be sitting here being your interviewer without her saving my life. She actually saved my life twice. Once when I had my motorcycle accident in 2016, and once more recently in 2021 when I had heart surgery. It turned out I had these valves replaced, and the surgery seemed to work out fine, except that they didn't notice that there was a blockage in my heart. And so the second day they were taking me out of the emergency room, putting me into the secondary room, but Mei Xuan came in early in the morning, detected I was actually dying, and I would have been dead in 20 minutes. They rushed me off to a second surgery to remove the blood clot.
And did she just observe how you were?
Yeah, she knew. She could tell by the way I looked from her experience that I was going to be dead in 20 minutes. Well, they immediately took me to surgery and opened back up my heart and removed this big blood clot.
And so the doctors found it. Yeah,
so anyway, she influenced my career by allowing
keeping
me
you
to
alive.
continue my career. But but of course, she's always been strongly behind me and helping me, giving me courage to do my work and follow my imagination and open up new paths and new directions, especially the quantum cognition work.
Okay.
Yeah.
Cool. So I have just one or two last questions. So I was also thinking about, in this purpose of this interview is thinking about mathematical psychology. And as you probably, more than I do, mathematical psychology has had its ups and downs. I think mathematical psychology is on a good upswing now. What do you think? And where would you like mathematical psychology to go? Where would you, if you were thinking about it and kind of pushing people, where would you tell people, where would you like to see it go?
Well, just to answer your question, I think the direction it's going is pretty good, that we're starting to build bridges with machine learning more, and we're also doing a lot of work in Bayesian statistics more, but we need to keep our cognitive science foundation and not lose ourselves to the machine learning or Bayesian statistics. We have to keep a foothold, strong foundation in cognitive science, But I think the field's really getting stronger and is healthy, and it's making impact. is making an impact on both the machine learning and neuroscience and statistical fields.
Mm-hmm.
You know? So
Where would quantum fit in? Do you think would you like to see it be more integrated in?
yeah, of course, of course. I mean, I would like. I mean, it's quantum. The quantum development is growing, but it's hard. It's a little more dispersed, and so it's hard to see it as well. You know, it's not like everybody in mathematical psychology is doing it. I mean, there are some people in math psychology doing it, a few, and there's some people in cognitive science doing it, a few. But there's also people in other fields doing it. Like a lot of people in physics are coming into cognitive science, trying to use some of these principles. You know, expanding on some of the work that I've done, or making new work of their own, and and people in economics and people in information retrieval, like Peter Bruza, my colleague that wrote the book with me on quantum cognition. You know, he's in information retrieval. So this work is appearing in a broad range of fields, and so it might be growing pretty well, but it's very dispersed. So there's lots of papers coming out. I'm asked to review many papers, and but they're in all kinds of different fields. You know, so it's not just cognitive science or There's a lot of them, and actually, Journal of Math Psych has a lot of papers in quantum cognition right now. But there are some in the cognitive journals like Psych Review and Cognitive Psychology and Cognitive Science and those journals. So it's growing, but it's more dispersed. So it's not easier to measure, I think.
So with mathematical psychology, you'd like to see more of it integrated, but keep psychology.
Yeah.
Keep
But another
science.
thing about quantum cognition is there's a big cost for getting into that game, because the quantum theory, it is based upon quite different kind of probability theory. And so there's a lot of upfront learning to be able to use it. It's a lot easier just to continue, with the traditional stochastic processes that everybody's been trained on. But, if you want to start using the Schrodinger equation or open systems, Lindblad operators and things from quantum theory, they look really strange at first. And so you've got to really, spend some time learning new things.
It's got real and complex parts.
Yeah. Take some upfront, commitment to get into the quantum cognition. And many people are afraid to make that commitment because they're afraid they want to do something more popular. What's popular right now, for example, instead of trying to strike out their own road like I did. Yeah.
So one last question, and you kind of already hinted at several of these, but so there's a common saying in science that we stand on the shoulders of giants. We've talked about some of those giants today, and I guess the last question is, who would you like to thank in this interview? You've talked about some of them, some people you'd like to thank and for your work today?
Well, of course, I'd like to thank you for interviewing me, and like I said, I really like to thank my wife for her strong support for me and for my health, not only my career but my health. And of course, early in my career, when I was postdoc and became a young assistant professor, Jim Townsend helped me a lot to get me started at Purdue University. But then when I got to IU, Rich Schifrin's been a really big supporter and a driving force helping me a lot these past few years in my career. So I want those people I should thank. And of course, I mentioned Tom and Amnon at the beginning. I have to continue thanking them. So.
And your students keep pushing you, yeah?
My students. I have to thank all my students, of course. All my students. They have been a big, advantage for me. So many great students, and all my collaborators. Have been such good collaborators working with me. So. I don't know if I should list them all, but.
No, but that's good.
Yeah. One other thing I just wanted to say was. Kind of some final words was that some final thoughts would be that I know that people know that the road of scientific research is very torturous and arduous and sometimes even boring, especially when we're encountering difficulties. So I hope the young people will face it bravely and work hard and avoid being opportunistic or even deceptive. History has proved that deception can only fool people for a while, and eventually it'll be crushed by the wheels of time and truth. One thing I always like to mention is quote by Feynman. He talked about what it is that makes science work. And Feynman, this is not the whole quote, but this came from one of Feynman's book. He said, "There's one feature I noticed that is generally missing in cargo cult science." Cargo cult science is pretend science, people pretending like they're doing science and not really doing science. He says, "And that's the idea that we all hope that you've learned in studying science in school. We never explicitly say what it is, but I just hope you catch on by all the examples of scientific investigation. It is interesting, therefore, to bring it out now and speak it out explicitly. It's a kind of scientific integrity, a principle of scientific thought that corresponds to an utter honesty." So that's thoughts I would like to give for future generations.
It's important to have integrity and this utter honesty of yourself.
Yeah, we have to try to seek the truth, not just fame and glory, but we need to find the truth in nature. We have to keep our eye on that, on the goal.
And not get fooled.
Yeah.
Or fooled by yourself.
Yeah.
Well, Jerome, congratulations. Thank you for this conversation. It's been my honor to interview you, and it's been great to always be your student. So thank you.
Thank you, Tim, for everything.